performance standards, without which requirements cannot be written, without which rocket ships cannot be built. And they will develop and validate the technologies that serve to reduce the medical risks associated with human spaceflight. So the Human Research Program is all about risk reduction. Our objectives are to establish the evidence base on astronaut health and performance for long-duration missions and weightlessness. And that's not trivial. We had 40 years of research, more or less, on people in spaceflight. But the evidence base was spotty because that 40 years covered a small number of people, each of whom might have been treated differently, and the statistical basis for the life sciences understanding was not always present because of other exigencies. We also have the objective of identifying the greatest risks and developing the optimal approach to the mitigation of those risks through countermeasures. We want to test space biomedical technology and medical care procedures on the actual astronauts in actual spaceflight, and of course actively collaborate and share resources with our international partners on space biomedical research. Those are the goals and objectives of the Human Research Program, which I'm here to represent. My summary of the effects of spaceflight on the human body, especially long-duration spaceflight, has been distilled down to one chart, which is impossible to read or explain in a brief period of time. Suffice it to say that there are many areas of interest: cardiovascular, sensory motor, what used to be called the neurovestibular, muscles and bones, which are on some charts lumped together because they have common effects and common changes, immunology, the immune system of the human body and how it responds to perturbations, both internal and external, and then the area that deals with the squishy stuff, the body fluids, the electrolytes, the hormones, and the metabolites, all of which have been shown to be affected by spaceflight factors, my most favorite of which, of course, is weightlessness, but there are others like isolation and radiation and confinement and so forth. Many of these factors, many of these changes, well, they're all documented. None of them are documented thoroughly. We need more investigations, more understanding of variabilities between individuals in terms of how they respond to the spaceflight environment. But many of these areas have been shown to have long-term consequences, and you'll be pleased to hear many others have been shown not to be such a big deal after all, including my own personal favorite area of investigation, which is orthostatic intolerance, the fainting astronauts may experience after even short periods in spaceflight. I spent most of my career working on various exotic countermeasures and treatments for this pernicious problem. And in fact, I have become a believer in the simplest solutions, two of which include the G-suit, the lower body compression garment, which suffices to protect the individual from many fainting episodes, and the other simplest solution is to stay seated instead of standing up if you don't have to. It's sort of like the old joke about the guy that goes to the doctor, says, "Doc, it hurts when I do this," and the doc says, "Well, then don't do that." That's how I've come to feel about my own area of interest, which is orthostatic intolerance. There's ways around it. Our physiological systems do change. Some say adapt with spaceflight, and those changes may affect operations in flight as well as returning to Earth. And those operations that may be affected include those that, not surprisingly, involve humans. EVA capabilities, the ability to move outside of the vehicle in a pressurized suit to do useful activities. And then, of course, the normal, which NASA calls nominal, and contingency activities during spacecraft entry into the atmosphere, descent and landing, whether it be the atmosphere of the planet that it departed from, the Earth, or the atmosphere of a different planet, namely Mars. And then the nominal and contingency egress, how one gets out of the vehicle when you have all the time in the world, and how one gets out of the vehicle when you don't have very much time. We have spent a lot of time working on contingency egress issues, especially earlier in my career, and preparing for space shuttle flights because of the concern of off-nominal landings or egress or bailouts at altitude for space shuttle crew members. And something that then occupies a majority of effort, especially of astronauts after long-duration flights, and that is returning post-flight to their pre-flight health condition, trying to get back to as good as they were before flight, which in some cases is impossible because the flights are now becoming long enough that just normal aging means that over that period of time you would have lost some small amount of capability that even normally, so you can't expect to get back what you would have lost anyhow after a space flight. But our goal is to facilitate the rapid post-flight return, to return individuals both operationally to their official duties and also facilitate their return to the activities of daily living so they can resume normal life back on Earth. And then long-term health issues, which is the predominant area of such research interests as the radiation problems, the radiation area, and also I think the bone loss area presents potential long-term health issues. And I think we can all agree that these changes must be thoroughly understood and mitigated where possible in order to manage the risks to astronaut health. We heard a little bit about human experience in spaceflight, and as General Bolden mentioned, we have had one individual that's flown long enough to make a very fast trip to Mars and back, 14 months, Dr. Polyakov on a mission in the mid-1990s. But the majority of astronauts have flown missions that are much shorter, and we've got, as Brett mentioned, the 6-month duration of a space station increment, which matches nicely with the outbound transit from Earth to Mars. And then this chart here, let's see, one of these is my laser, isn't it? If you can see that little red dot, this illustrates a sort of a histogram of flight durations. These are all individual exposures. Each of these lines is one person's flight, a contiguous flight. As of a few years ago, last time I did this tally, flights of 0 to 450 days, these are roughly 1 month hash marks here, and you can see that the majority of human exposures to spaceflight is in the order of 4 to 6 months, as Brett mentioned. We also mentioned the fact that, Brett mentioned the fact that Mars missions may be 30 months long, so you will ask, as I might ask, what about this? How about the area that's not covered in the graph? How about the area that indicates no human exposure experience? Are we concerned about that at all? My answer is no, for 2 reasons. Number 1, I'm not going to be going. Number 2, you should forgive this chart, but it illustrates one of the truisms of biological research, and that is the physiological or biological adjustment to a new environment occurs fairly quickly and reaches a steady state. In many areas, not all areas, and I'm sure all of us can think of areas that are exclusions to that policy. But in many areas, we believe we're seeing. Oops, darn it. We believe we're seeing adjustments to normal physiology within hours, days, weeks of assuming occupation of the microgravity, the weightlessness environment in the area of the sensory motor system. This is a Skylab era chart, so they still called it neurovestibular back in those days. The fluids and electrolytes, the cardiovascular system, red cell mass, all these areas were studied very thoroughly on Skylab. And other areas that show less adaptation, of course, during the period are things like radiation effects and bone and calcium metabolism, bone and calcium metabolism, that is bone mineral density, and of course not shown on this chart, the psychological, psychosocial factors, behavioral health and performance. Some of the physiological variables do seem to reach an adapted state within a relatively short period of time. Others do not. Others continue to potentially continue to get worse the longer that the exposure is. But for those that are shown to be adapting, I think we can make the case that short flights on the order of 6 months, perhaps even 4 months, are long enough to help us to understand the effects of spaceflight on the body and also to test countermeasures that should then be useful for longer flights of a longer duration, of almost any duration you want to suggest. So in answer to the question that Dr. Bolden fielded earlier, sorry, General Bolden, I shouldn't demote him to doctor. General Bolden fielded earlier about how long should we fly flights and can we make flights longer. It is operationally, of course, perhaps possible to fly flights longer than 6 months, but at least some of us in the life sciences area would say don't, because we need more than long flights. We need warm bodies exposed to those flights to understand the effects of those same flight environment characteristics on a variety of people in a variety of circumstances, testing different countermeasures. And so we would actually support 4-month flights if we could get them, but of course that would increase the number of Soyuz resupply missions by 50% that are already kind of expensive. So we're probably going to compromise with the 6 months, but please don't let's stretch it out beyond that if we don't really have to for some very good purpose. I can think of good purposes for stretching it out, but I'm not going to tell you what those are at this time. If we do fly people to other planets, we'll have the problem that Brett mentioned earlier, and that is what happens when you get to the planet. You have to do useful work in a deconditioned state, We already have examples of people landing after long periods of time in space flight. And given all of the caveats, you care to mention the fact that it's Earth, not Mars, the gravity is 3 times higher, it's not the same thing as going to Mars when you land back in Kazakhstan. Still, there is evidence that we are not in the best condition for landing on a new planet and immediately going to work and doing important scientific and operational activities. In fact, we send people off to periods of rehabilitation back here on Earth for weeks to months after their long-duration flights. Without that kind of capability on Mars, we'll have to make other kinds of approaches and other kinds of plans. Having said that, though, I'm reminded by my colleague Don Pettit, who has had a chance to experience this environment at least once in an upcoming another opportunity. We've actually done this experiment. We've actually landed a crew after a 6-month transit on a planet and forced them to function on their own, and they were able to do quite nicely. They were able to do important activities and maintain their function until they were provided backup, until they were rescued. All 3 crew members on the Expedition 6 landing in Kazakhstan, which went ballistic and landed off course, they exhibited reduced capability from limited mobility all the way through voluntary immobility. It felt so good just to lay down in one case and not do anything that's what that individual preferred to do, while others may have moved around a little bit. 30 minutes worth of work was accomplished, and Don tells me he did about 30 minutes of work, and it took about 5 hours to do it, but there was no real rush, so it was okay. And the unencumbered weight, just remind you that the unencumbered weight of a person on the Earth is approximately what the weight of a person wearing a heavy spacesuit on Mars will be, so we're probably not too far qualitatively from mimicking the condition of astronauts landing on Mars in this post-landing scenario. That was an investigation that I would like to have proposed, but I suspect if I had proposed putting astronauts after a long-duration flight into a desert on the Earth without actual support for up to 5 hours, I would have been shown the door very quickly. No way of getting that through the human ethics review process. But we did do it sort of serendipitously through the operations environment. And that inspired some other work. We have been looking, we in the life sciences have been looking at the problems of getting to, the biomedical problems of getting to Mars for quite a while now. We did something called the Mars Surface Analog Project in 2002, 2003. That was a JSC internal project. Several workshops, which actually preceded the Don Pettit experiment. And we like to think that we at least allowed ourselves to be prepared for the activity that Don presented with us de facto, and also we provided at least one investigation's worth of inspiration to an investigator who is now assessing in a quantitative means how people respond to, or how people are able to accomplish activities, operational activities post-flight. That's Dr. Jacob Bloomberg and his functional task test activities post-space station missions. As I mentioned, the Human Research Program was established in 2005 with a Mars focus for human research and technology. That is a definite plus in the column of exploration-related NASA biomedical problems planning. And we have since then tried to understand just the question that was asked earlier, that is, how long can we fly in space? Through at least one workshop in September of 2009, we talked about the extension of ISS, biomedical aspects of extension of the ISS up to 9 to 12 months, as well as simulation of a Mars mission on ISS. And we've also been part of an ongoing activity that you'll hear a little bit more about this afternoon. Pete Hasbrook will brief you on activities within NASA, the ISTAR project. The ISS is a test bed for analog research. But HRP is not surprisingly a major part of that activity, since everything we've been doing since 2009 is Mars related and is focused on Mars. So you'll hear more about some of our plans for that coming up this afternoon. So what does ISS offer to Mars related to human research? Well, the strengths are weightlessness. I think until we have warp drive or something like that that can get us someplace with a constant G load, we're going to be seeing astronauts exposed to weightlessness for a long periods of time. The 30-month conjunction class mission will begin with a 6-month or so transit to Mars, and that's what we see with the station crew all the time. So we can be evaluating both the normal physiological responses to spaceflight and the countermeasures to be developed and validated. And for psychological and psychosocial and behavioral health aspects, there is nothing like a good simulation to understand what the problems might be. We might make the case that the space station itself is an excellent simulation of a Mars vehicle because unlike many other analogs that you might find on the Earth, using graduate students in laboratories at a university someplace, for example, the space station provides people very much like astronauts, doing very much space-like activities and something very much like an actual spacecraft with actual meaningful risks. The vacuum outside the door, for example, which cannot be duplicated conveniently on the Earth. So the psychological factors and the health and the human factors of putting people in space flight on the space station are very, very, very relevant to preparing for trips to Mars. Of course, the weaknesses are easy to pick up. We are shielded from deep space radiation, so the space station is not a good place to do radiation research, especially relating to the cosmic rays of deep space outside the Van Allen belt, but there are other radiation issues that can be addressed on the station. And you will all quickly remind me that the space station is in a low Earth orbit, not going to Mars, so it is close to Earth. There is no communications lag yet of comparable magnitude to going to Mars. And Earth is always just outside the window, so in case you're afraid you're going to Mars, you simply have to look out the window and be reassured that the Earth is very close. So there will be some limits to the psychological realism of pretending to go to Mars on the International Space Station. I maintain there's a great deal that can be learned from those limitations. So in conclusion, the human research on space station does support crew health and performance for current and our long hoped for future space missions. Things we are learning on the space station right now in terms of these topic areas will be relevant to planning and preparations for going to Mars. Pre-screening, that is selecting the right people to go to Mars, and a great number of our medical and physiological problems of spaceflight can be addressed through pre-selection. It's one of the least popular topics to discuss, especially with astronauts, but there may be ways to decide who can fly to Mars based on the characteristics of their parents and grandparents, something that we have very little control over. Exercise is the favorite countermeasure to almost anything that ails you in space flight, and we are learning how to do that more effectively, more efficiently, and deciding where it is actually limited in terms of what it can do for us. Nutrition picks up a lot of the slack that exercise may leave. Well-nourished individuals are going to be healthier, and certain kinds of nutrition can act to reduce the effects of radiation and other insults from spaceflight. Pharmaceuticals, ditto, can provide some support. And the operational workarounds, like I said earlier, if you get dizzy when you stand up, then don't stand up. There may be ways to fix many of the operational problems we address on long-duration flights to Mars with the appropriate architecture and the appropriate design, like for example, making the lander able to accommodate the crew members for several days while they get their Mars legs, instead of giving it a short duration life support system that requires them to get out and trudge across the Martian desert immediately after landing in a deconditioned state. And other countermeasures as needed. We are constantly interrogating the crew members and the flight surgeons about the issues that they confront, so we can be developing the appropriate countermeasures, the appropriate treatments for those situations. So I believe that's my final chart. I'm delighted to, like I say, be part of this panel and look forward to your questions during the Q&A period.